Hi everyone. Today's seminar is on profiling function vectorization in Matlab and Octave. Now, although this will be based inside of Matlab and Octave, and a lot of the tools are specific to how to optimize, specifically in the direction of vectorizing functions, this is a far more general talk in terms of profiling and understanding how the way that you're developing your code is going to behave in terms of accessing memory and the speed of processing and the number of resources required. So this relates to a few other seminars that we have, our YouTube channel, including getting the most out of SHARCNet, understanding how the scheduler works and how the properties of your jobs will get you into the running state more quickly. It also relates to other seminars that we have specifically to Matlab, as well as other seminars on profiling, and even some seminars on vectorization. Now, in this presentation, we're basically going to go through an example. We'll start off by an example, and these icons over here on the right is just an overview that I'll talk about these functions. Once we talk about the functions and how we cascade through optimizing the vectorization of a basic procedure, then I'll go into Matlab and we'll go over these examples step by step, including how to profile the results of the different steps that we're using. After I go through the examples in Matlab, then we'll go over to the cluster and we'll actually submit these jobs with the profiling in them and perform them in Octave to see how they'll actually behave in the environment that we intend to run them in at SHARCNet. So again, in general, this will really get to the idea of what it means to form your code so that you're optimizing the way that it relates to the cluster. Remember that a scheduler just sees multi-dimensional rectangles, and what we want to do is get code to perform as quickly as possible, but also reduce the resources that are defining how much memory is required or the number of cores that are required. And what we find, especially in Matlab and Octave, is that by vectorizing, we can reduce all of these resources and get the fastest time. So this is the basic example that we're working with. If these two rectangles actually represent a three-dimensional data array in Matlab. So we have a bunch of rows across here, and then a bunch of columns, and then we have multiple pages moving this way. This example is basically what we want to do is take the mean of each of these rows and then subtract that mean from the row. So typically, what we would like to do is just say, well, the out data equals the data minus the mean of the data. Now, this doesn't work because all that we want is the mean across the rows and then to apply that to every instance in the row. So just running this function here, although it has the mean and we're operating on the data, and then we're taking the mean of the data, it says nothing about which direction the mean is being calculated in. And if you calculate a mean, then it won't necessarily apply to the full data in the right orientation. So the first thing that we try to do is perform an explicit loop. Now, what this explicit loop will do is computationally demanding, and what will basically happen is you would do a nested set of loops for all of the rows and all of the pages. You would calculate a mean. So along this row, calculate the mean, and then subtract that mean from this row. Move on to this page, calculate the mean, perform the subtraction. Move down a row, calculate the mean, subtract, move down a row, calculate the mean, subtract. Go all the way through this way, and then all the way through that way. And that represents this looping through the rows, looping through the pages, each time defining which values are going to be included whenever you are performing the mean and then subtracting it. So this is the example of an explicit loop performing a very simple operation. all that we want to do is remove the mean of the rows and all the instances in our multidimensional array. So this performs the mean perhaps millions, thousands of times, depending on the size of our array. And as you scale up, the number of times that all these calculations have to happen increases. Now, another thing that we can do in this case is actually increase the number of cores being used. And we do that here by, instead of doing an outer for loop, we can then do an outer parallel for loop. Now what that means is that the outer loop described here could actually be done on multiple cores simultaneously. And then we can perhaps increase or decrease the amount of time that this entire calculation would take by increasing the number of cores that we're using to perform it. And really the only changes in the code are changing the outer loop to a par4 and then accounting for some of the complexities that happen within there. But otherwise the code is the same. In this case, we might be able to increase the speed if there isn't too much overhead by performing the same number of calculations but spreading it out across cores. Now, another alternative is really we can start introducing the vectorization of a function. That means that in this case, we won't necessarily just be calculating a single mean here. What we'll do is we'll calculate the array of means along this in one call. And that's what we see here. That now we're calculating the mean of data across the second dimension. The second dimension being these columns, we create in one call a vector of all of those. And then it also calculates it on all the pages. Now, once we calculate this array of the means of all the rows for each of the pages, then we just have to loop through the columns of the data and then subtract that mean. So that takes this array and passes through this way, performing a subtraction at each point along the way. Now, in this case, you're performing the mean substantially fewer times, but it is a larger mean as you're calculating it along all of the rows and all of the pages. Now, we can extend this a bit further. Now that the mean is calculated on the vectorized, along the second dimension, we don't actually have to calculate it every time inside of this loop. What we can do is we can actually take it outside of the loop, calculate it once, and generate this intermediate array. So what this is doing now is it's actually calculating this array one time, not calculating it again each time, and then just moving that array through. Now, the difference between this and the last one is that we might be allocating a lot more memory while doing this, even though it no longer has to calculate it every time that it's within the loop. So this could substantially decrease the amount of time that the calculation takes, but might increase the amount of memory that's required to perform it. Now, the next thing that we can do is actually generating a full-size array and just perform the subtraction once rather than subtracting it along each column of the array. And we can do this using the function repmat. In the case of repmat, we no longer need a loop at all. What we're doing is we're saying we're going to take the data, and in one instance we're going to subtract an entire array that's the same size as the data, and we're going to generate it using repmat. Now, the thing that we're expanding is the mean of the data. So in this example, what we're doing is we're doing the same thing. We calculate the means along the rows, and then we actually expand this out so that this array is the same size as that. This array is the same size as that one. then we take this whole thing and we say, go over here and subtract it. So we have the data. We're subtracting the expanded RepMat version of the mean along the second dimension. Now, this can be substantially faster than any form of looping, but it definitely increases a large intermediate array that can put more demands on memory than might be desired. And then next is the final step. So how can we basically do this, perform a single subtraction without looping anywhere on a three-dimensional array without the need for expanding the full-size data array that could increase the memory requirements by several times. To do this, we'll use the binary expansion, so BSX_fun. And here we see the example. Again, there is no loop, but what we're doing is we're saying we're going to binary expand the minus function. And what we're going to do is we're going to take the data and we're going to subtract the mean along the second dimension. So what this looks like is you calculate the mean here, you calculate the mean here, and then instead of expanding out this intermediate array, you say, just take this and then subtract it across the entire thing, forming the minus with BSX_fun. Now, if this works, what we've done is we're only performing one minus the whole time, and there's no need to expand the entire array out, increasing the amount of memory. Now, in terms of what this would look like to the scheduler, is fantastic. It's still a serial job being performed on one core. It's only happening once, the subtraction, the actual calculations that are taking up all the compute, the mean and the subtraction. It's serial, and it doesn't require an intermediate array that could increase the amount of memory required by this task. So here's a simple example. And what I'm going to do now is I'm just going to go over to Matlab, and we'll start going through these examples. So here I am over on Matlab, and I'm just going to go through and describe each of these steps. So first of all, to show you the data, if we go to load and then EEG data.mat. So this example data is taken from EEG research, where we record the electrical activity coming off of the scalp. And we record it on multiple locations, hundreds perhaps of locations, and we record a microvolt value every couple of milliseconds or so. And then we often chop up the data so that there are the rows are the channels, the columns are the time points, and the pages are individual slices of data. So if I just load this data set, we can give you an example of why we want to actually subtract the mean and then what it looks like once we do it. So from here, I'll say figure waterfall EEG row data, all rows by all columns, and then I'll just plot the first page of this data. Okay, so what we see here is a waterfall plot of basically the first page of this data. So a row is presented here, and then these are the columns going down this way. Now, what's happened here is the data that we recorded has an offset of microvolts that are massive compared to the actual signal that we're looking for. So actually, each of these straight lines has information that we're interested in. But relative to their offset, the distance from 0, they're very small. So what we'd like to do is just remove the mean of each of these rows here and then replot the data. So as an example, we'll just take this, and then I'll perform the explicit loop operation on the data, generating out data, where we define each row and each page, and then explicitly subtract the mean of that data and then generate the out data. So let's highlight that, press F9, and then it's going through and running, and it's done. So what we can do now is I'll just replot this, except it'll be the out data. Okay, so this is more what we're looking for in terms of being able to tell what was in there. So what had just been straight lines, if I can get the orientation right here, is now a representation of EEG data that I can see if I can get this orientation right. There we go. So now what we can see is actually the oscillations of EEG data along space, and we can see that this is actually a representation of an eye blink, where these sensors sort of at the front of the head have this big burst in activity, and then this is actually going from front to back, where over here it's the back of the head. So now we can see the actual representations of the voltages that we're interested in, rather than just the offsets that we were looking at before. So this subtraction of the mean is the example that I'm going to use for this entire procedure of vectorizing those functions. Now, the other thing that we want to do is, while we're moving towards more and more vectorization in this code, we want to actually kind of have an understanding of how we're doing in terms of the amount of time of the calculation, and also take a look at the breakdown of what functions are running, how many times they're running, and how much time specific functions are taking up on the compute cores. So we have these full scripts that I've generated for each one of the examples. This one is the explicit loop, and what I'm going to do is I'm just going to F9 and then let it run. And while it's running, we'll just give a breakdown here. So I just clear all, so make sure that the workspace is nice and clear, and then I turn the profile off. So the profile function is something that will be running in the background, and you can toggle it on and off. While the profile is on, it will keep track of the functions that are running, how much time they're running, also how much time the children of those functions are running, and keeping track of the time within that function and within their children, et cetera, et cetera, et cetera, and then the number of times they're running. Now, I get started just by turning it off unless there's a profiler currently running at the onset of this script. I then load my data file, and then I turn the profiler back on, and then I start a tick. So tick talk will return the amount of time between those two functions. So I perform a tick, I perform the operation that I'm interested in. This is the explicit looping, going through all the rows and columns and subtracting the one instance of the mean on each iteration. Once it's done, I hit ask for talk. Talk without the semicolon will just spit the amount of time out in the command line, and that's what we see right here. So between the tick and the talk, this took 4 seconds. Now, this code can just be left in the script, and this is important because what we're going to do after exploring this in Matlab is we're just going to go over to the cluster and start submitting jobs in the system, the cluster that we're interested in running this code at. And then what we'll have is in the output logs, we'll have this specifying, how long Octave or Matlab actually thought it took. We'll also have the log file, the epilogue in there, giving some information about it. The last thing that happens is that a variable structure is stored that's containing all of the profile information. So this gives you a hierarchy and a structure of all the functions that performed in the time, and as well as their counts and the amount of time that each one took up. Now, this gets placed into a structure, turn the profile off, and then we actually save that structure so that we can then take a look at it after. Now, this is important because once we go to the cluster, we want to actually, instead of even doing the profiling within development node where we're doing it interactively like I'm doing here, what we're going to do is just submit jobs. So they will occur in the exact environment that we want to start running the production scripts at. And we'll see the profiling in exactly that context. Now, this is an important difference because the the setup of the actual compute nodes might be very different from anywhere else that we're running, and we want to see how it's performing explicitly there where we want to do our production work. So now if I go into the MATLAB command line, I can see that there is this structure here. Now inside of MATLAB, I can then start exploring it. I can say profile, view, and then ask for the structure that I created. So the subtract mean loop. And what this will bring up is an interactive window where we can take a look at it, and then we see here which functions ran. In this case, it's only the mean. But of course, the whole issue here is that the mean ran almost 122,000 times. The amount of time it spent in there was over 2 seconds. And then we can see that in the total time. Ended up being 4 seconds between the tick and the talk. Now, in this window, you can then go down into different functions, and you can see what actually ran within those functions. Now, this example of subtracting the mean is purposely one of the most simple examples we can have, or at the top level, it's really just the mean that was calculated. But hopefully this will relate to more and more complicated methods, and you can keep going down into specific functions to see what was happening within them. And then you get the exact lines that it spent time on for these specific things. So what we see here is, basically this one took 4 seconds, and we see that the reason it's taking so long is because it's performing so many mean functions and then subtracting them. Now, let's regress just a little bit. One thing we have to be very careful about whenever we're performing any sort of large array math, particularly on the cluster, is how it's relating to the memory. Now, we just did a pretty good job. What we did here is, we pre-allocated this array that's going to be generated inside of a loop. But I just want to give you an example of what happens if you don't pre-allocate this array. You're perfectly allowed. You're capable of just starting this array inside of a loop. MATLAB will always underline it, and it'll say, listen, the variable here appears to change size on every loop iteration. It doesn't seem to be so bad at the outset, but really what's happening is every time that this function happens, MATLAB is reassigning the entire memory. So not only is the memory growing, it has to reassign the memory. This can take substantial amounts of time, and the amount of time that takes increases on every iteration. Now, performing this in the cluster can be exponentially worse because the memory doesn't take the same form as on the local computer, and there can be several delays that add on to here. Now, this might run perfectly fine if we're running it locally, but then you take this mistake of not pre-allocating the array and running it at the terminal, and something that may have taken minutes as a mistake locally might take an hour over on the cluster. So what I'm just going to do is I'm just going to run this script and just see how much the difference is if I run it locally here. So this one's now running. And what previously took 4 seconds, just by not allocating, doubles in time. Now, we can then take a look inside and see, the same number of functions ran, the mean is the same calculation, but the problem is that having to reallocate the memory on every iteration slowed it down and doubling the amount of time here, which may be substantially more over on a cluster. So this is an obvious mistake to not do. MATLAB will always give you warnings about this, but if you're programming in Octave, you might not see it as explicitly. Now, the next thing that we could try is, let's say, we got this with the explicit looping, it happens in 4 seconds. But let's say we have access to the parallel computing toolbox in MATLAB, and that gives us the ability to perform a par 4 loop. So in this case, what we're going to do, everything is going to start off identically. We clear everything, we turn the profiler off just in case there's one hanging around already. We're going to load the data, start a tick, and then open a Matlab pool and then do a talk. Now, the reason that we're going to time this is that doing parallel computation has overhead, including just setting up what the parallel, what the workers are going to look like. So we'll do a tick talk just around the actual setup of the 8 workers that we're going to set up. We start the profiler, and then we do another tick. Now we change the code a little bit so that we can run the par for. What this is going to do is the outer loop, the one that's doing the rows, is going to perform 8 at a time. And then we'll get the talk at the end, and then we'll save the profiling information, turn the profiler off, and then actually explicitly save to a file. And then we'll close the Matlab pool. So I'm going to highlight this, and F9, and then here it goes. So originally, this loop operated in 4 seconds before the pre-allocation. So the initial elapsed time was 7 seconds. That's just to build the workers to do this parallel computation. Now, in this case, the overhead alone doesn't make it worth it because the overhead takes more time than the actual computation that we found before. But once it's done, we get a bit of a speed up. In this case, increasing 8 cores isn't worth doing in any way. Now, there may be some other configurations that we get to down the line where actually increasing the number of cores will benefit this calculation. But obviously, at this case, it's not something that we're going to pursue. Now, the next example is we're going to start actually vectorizing the code. Again, the beginning is identical. We clear it all, turn the profiler off, load the data, turn the profiler on, start a tick. We pre-allocate the exact same array that we're looking at before, but now we're only going to do one loop, and that's a column loop, where the first case of vectorization is actually doing the native vectorization of the mean function. That is, we're going to perform the mean on the data along the second dimension. So this is going to reduce the second dimension to one value based on calculating the mean. And then we're just going to loop through and subtract that mean from every column. And then we'll do the talk, et cetera, et cetera, et cetera. So we'll just go ahead, F9 this one. And then what we'll see, this one actually takes quite a bit of time. Even though what we're doing is we're reducing the number of iterations that have to happen, we're reducing the number of actual calculations of means to only the number of columns in our data array. We're no longer doing it for every row and every page. This calculation of the mean is a substantially larger calculation. So now this has jumped up to 25 seconds. Even though we've reduced the number of iterations substantially, right? So if I say now that I want to do prof view in this prof view, and then it's p subtract the mean column loop. So we see here now the actual mean only happens 500 times. That's the number of columns that we have in the data. But the amount of time it's spent in there is substantially more than before. So this is saying that the vectorized mean takes longer than the mean that we calculated just along the one dimension. So luckily, this calculation of the vectorized mean is the identical calculation on each iteration inside of this loop. So what we can do is instead of calculating each side, we can create an intermediate array that holds the mean in the second dimension. So the column mean equals the mean in the second data, and then we can just use that and subtract it. So now inside of the column loop, we're using one instance of the vectorized function and then just subtracting it. In this case, the calculation of the mean only happens once. The calculation of the minus happens 500 times. And what we're doing is we're increasing the memory required by holding this intermediate array. But let's just see how it performs. 9. So here we see the performance has gone down significantly. Our fastest so far was 4 seconds on the explicit loop. And now by doing the column loops and using an intermediate array to subtract, we're now down to 0.5 seconds. And then if we prop view CLI for the intermediate, we see that the mean is only calculated once. Its duration is 0.1. So we're doing great so far. Now, the mean is calculated once, and then the subtractions are calculated 500 times. So what we want to look at now is how can we go from calculating the subtraction 500 times, even though the mean is what's taking up most of the time, to only calculating the subtraction once as well. And we can do that initially. We can have an example of then going ahead and doing this one in parallel if we would like to. But let's go ahead and just get rid of the loop altogether. Again, starting with clearing all, clearing the profiler, loading the data profile tick on. Now, we pre-allocate the array again. And then, actually, we don't need to for any reason now. We then just take the data, perform one subtraction, where we take the vectorized mean along the second dimension, and then expand that single row vector that has the single column vector that has multiple rows and multiple pages, and then expand it out to the size of the original data second dimension. So then just spread that out across columns. So in this case, we perform the subtraction once, we perform the vectorized mean once, and then we generate the out data. Let's just see how this one performs. And now we have it down to 0.2. Now, let's just take a look at something here. So the downside to this is the number of calculations is great. This is still a serial procedure. We aren't increasing the number of cores at all. But what we're doing is we're creating a large array with this repmat. This generates an intermediate array that's the exact same size of the data array itself, and then uses that array to do the subtraction. Now, let's just take a look at what happens if we can actually do the exact same calculation, but now not using an intermediate array. So the way to do that is if you get to a point where repmat is working and you don't want to increase the amount of memory required, then I can get rid of that pre-allocation as well. Do the same setup. Now the out data is going to be performed by doing the binary expansion of the minus calculation on the data minus the mean along the second duration. So the vectorized mean along the second duration. So calculate the mean along the second dimension. You want to subtract that from data. This BSX finite minus will expand that out along that dimension without creating an intermediate array. So what does that look like? 9. And now we're down to 0.1. So sort of at this point, we can't get going all that much faster. And we're doing a great job. Everything seems fine. What we've done now is we've reduced all the calculations down to one instance, and we haven't doubled or maybe quadrupled the amount of memory required by the job, and it's all still being done serially. Another thing that the profiler can do in Matlab, although this takes a substantial amount of time, so until you're ready to actually get into the specifics of memory, it's not really worth adding. Whenever we turn the profiler on, we can also switch the memory toggle. This will also monitor the memory that's being allocated and removed on every function in every iteration. So I'm just going to add the memory to this profiling, and then F9. Happens pretty good. And then we'll do the prof view, except now this is the subtract mean BSX, I called it. What this has done is it's now added the self memory, the peak memory, and then the freed memory of all the annotations, including the number of calls and the amount of time it's spent in each instance. And what we see here is, this mean is calculated once, everything looks great, and there's a certain amount of memory that's used. It doesn't seem outrageous. Now, if I go back to the rep mat, where we actually expand this out, and then I turn the memory flag on for this profiling instance, and then rerun this one, now we'll see what ends up being added. We're pretty happy with the time in this calculation, but remember, once we get onto the cluster and we have to take into consideration getting the job into the queue, we want to make sure we're also very aware of the dimension of memory in getting this job into the running state, that we aren't really decreasing the amount of time at a penalty of increasing too many resources requirements on the system. So it's done. Did a pretty good job in time. And as for profile viewer, and this is now subtract the mean rep mat. And what we see here is really that the one calculation of the mean is using the same amount of memory as it was in the BSX fun, but the instance of rep mat is using substantially more memory and allocating more self-memory. This is something that we'll have to take a look at on the cluster to see how much of a difference it actually accumulates to when running it in the context that we want to do in the production setting. So, given all this, what we can do now is we can just go over, let's go to Kraken. So, because really in Octave we're going to be doing everything serially. We won't be testing any of the parallel functions because we found that in terms of parallelizing this function it's not necessary because everything can be vectorized. So we'll go over to Kraken and to do some parallel processing or serial, and we'll just test some of these scripts. So Shard at Kraken SHARCNet.ca. Okay, I'll go to my work directory, Shard, and then this is, what's it, CD. Okay, so here I am inside the same folder that was transferred over to my work directory on the cluster. And then we see that the functions that we just went over, the process of getting more and more vectorized in terms of calculating the mean of the rows, all of those are just scripts that are listed here. So on the cluster, let's just do it backwards at this point. We'll run the best performance that we found locally and just see how it runs in the actual production environment on Kraken here. So we want to run it exactly the way that we're going to be running it in production, so we're going to submit it to the cluster. SQ sub, this is a quick job. We'll give it 5 minutes. The output we will call we're profiling, subtracting the mean, BSX.out. And then what we want to do is start up Octave, and then we're going to run the script submean bsx fun.m. So this is pretty much exactly the way that we're going to do it in production. Now, inside of this script, we know that we started all the profiling, and so that will all happen, and it'll spit out the right things to the output file. I'm going to run it. I just realized this is going to generate an error for a bunch of reasons, one of them being I didn't start up Octave. Module load Octave. Of course. Okay. Now the other reason, because I'm so natural at this, we have to actually say that 5 minutes is the runtime. The output is profiling, subtract the mean using the binary expansion. I'm going to ask Octave to run this script. And now, hopefully everything is okay. Submitted the job. Execute jobs. Let's take a look at what's going on. And it's in the queue. So I'm just going to give this a second and see if it gets inside the queue. So again. And if it doesn't get there soon, I've pre-calculated a bunch of these, so we can just go look at those. Now, again, we can't emphasize enough how important it is that whenever we're planning how a function is going to perform, that we take into consideration that these schedulers really only see multidimensional rectangles. That is, if you have a memory spike somewhere in your code, you have to specify whenever you're submitting your job the maximum memory that's going to be required for that job. Also, the maximum number of cores and the amount of time. Generally, what we're trying to do is reduce the amount of time, but in terms of getting into the scheduler and having the system run as efficiently as it can as a massively shared resource, what we want to do is reduce all of those dimensions as much as possible. And so far, what we've seen is that the BSX fun is really the way to go for this. So now it's done. It made it through the queue. Probably went in the R state somewhere along there. And now it's done. And then what we see here is that it generated the output file that we wanted. I go and just open up this output file and say that subtract the mean, bsx.out. So here we go. Between the tick and the talk, this now took 3 seconds, which is actually substantially longer than it did locally. But this is still in the context where Matlab or Octave is accessing a completely different form of memory than it was locally. The amount of memory I actually use isn't listed here. Just the amount of time. So I'll escape out of here. And then what we can do, I'm just going to go over to Advanced, LS, and then open the initial one that we had here. So whenever I ran this recently before starting this webinar, a similar thing. The amount of time between tick and talk was down at 2 seconds, and the amount of memory that I required was over 700 of the default 2 gig memory request by execute jobs, and that's the default. And again, remember that if this has to increase too much, then this becomes a problem on the cluster end, not only in terms of having to request more resources, but the amount of memory required can slow down the processes on the cluster. So I'm just going to take a look. One of the things that ended up happening, for example, the last time locally, what we're able to find is just by looking at the amount of time it took to process the function. If we did the repmat expansion of an intermediate array on the entire data and then just did the one subtraction, the amount of time was perfectly fine. But what we find is that the actual memory, in this case, if we just do the subtract the mean, I ran this earlier, generated the output of the rep mat, then what we find is that this function actually runs out of memory. And it runs out of memory because of that intermediate array. So this function isn't able to run with a default 2 gig allocation, even though with BSX Fun, it was, under half of the memory requirement. This job got terminated, and then if we expand it out to request 4 gigs to SQ sub, then the job runs in about the same amount of time, but we've had to double the amount of memory required for this. Now, this is also an issue because what we want this to be able to do is scale up to larger and larger data sets. That's sort of the point of moving over to the cluster. And this change in the amount of memory required might get worse and worse and actually slow it down substantially. And we'll escape out of there. Now, we'll go back over to this presentation. So we've gone through and, with this very simple example of just subtracting the mean from an array along a dimension, we see that BSX Fun is very valuable in terms of vectorizing the entire thing, calculating one mean, calculating one subtraction without a massive expansion of the memory requirements. Now, the issue is that BSX Fun is only capable of doing specific functions, native functions like the mean, minus, plus. But what in the example where we want to do something like the correlation coefficient, where inside of a loop you want to do the correlation coefficient of a certain dimension on a certain dimension? You can then go and try and do it in parallel in this case, because this function might take substantially longer. It might now be worth doing it in parallel, but there's no way of just giving this function over to BSX Fun and then performing it one time, unless you actually go inside the function and then rebuild it. Now, we won't get into many details, but basically what we're doing here is the exact same calculation. But instead of trying to enter core coef, which is the native correlation coefficient in Octave and Matlab, we're actually performing the correlation coefficient explicitly, where each of the modules inside of this function are calculated using BSX Fun, and this just has to happen once. So in many cases, you'll even find that native functions within within Matlab and Octave can actually be improved, that you can perform the exact same calculation, but going inside and changing the internal structure to include BSX Fun. Now, this is a great example to try out in Matlab and then send it over on the cluster. And this is the sort of thing where we've found massive time improvements, functions going from an hour to a few seconds in many cases. And that really concludes the presentation on optimizing using profiling function vectorization. Of course, if you have any questions about this topic, if you want to try these out on your own data, never hesitate to email us at help@sharcnet.ca. I'm glad to answer your questions and even test some of these procedures out for you if they apply. And thank you very much.